Okay, guys, as promised, we have our friend Jerry Boggs here to talk about generators and generator standby systems for commercial buildings. He has a great presentation and a great experience. Big experience in the generators. Like I told you before Jerry comes, if you guys, when you become experts in your field, which you will be calling on generator to help on Jerry to help you size and specify the right fuel for your generator. So Jerry's going to have a great presentation. He also shares the presentation with us, so right, so it will be on the network after he's done. So I hope you guys will enjoy it. Just FYI, I think we have 9 of you guys and 7 are working, right? Am I right? Or 7 of you guys are working out of 9 with 3 are not. So that will give us 6. 6 are working.
Very good.
We have Parson, we have Egan, North side, North, where are you working? Peoples? Do we have Peoples? So, but no. Kerry, where are you working?
Ben Franklin.
Ben Franklin and Ace, Parson, Egan, Mina, and I keep forgetting yours. Northern Electric. So we have a bunch of guys who are working. So 3 to go. If you guys are looking, we have the best and the brightest here. So all right, I'll let you go.
Well, thank you very much, Chad. Again, I run a very informal presentation. If you have questions, either raise your hand, get my attention somehow, and ask it, and we can talk about it. I'm here for you guys. Anything you need, I'll try to get you. If I don't have the answer, I will get it for you. Okay. Today's agenda. Can have a brief introduction. Yeah, get rid of that.
Yeah.
Okay. Discussion of the product, different types of products that we have to offer and how you can apply them. Common options. We're going to talk about transfer equipment, different types of loads, design types, and common issues of the day, which there's quite a few of them actually. Starting out, who is Interstate? We are formerly Interstate Detroit Diesel. Now it's Interstate Companies. We cover about 10 states. Now this is a little outdated. We just added a couple more. We have 18 branches throughout the Midwest. It's kind of a map of our territory. We've added some territory down in this area. We've got half of Missouri now and about half of Illinois. We don't have all of Illinois. And 18 branches across that network. We are actually, Interstate Companies is divided right down the middle. You guys go up and down the freeways in 35 and even out as far as Billings, Montana. You'll see Interstate Power Systems. That's our group. You might see I-State Trucks as well. That's also us. That comes under the heading of Interstate Companies. We're privately held. Gordon Galarno owns it. He's also the chairman.
You guys have a copy of the presentation too in the folder.
Yes. MTU. MTU is a relatively new brand name. The former name that you might recognize, obviously, is Detroit Diesel, one of the 3 big engine houses in the world. They are currently owned by Rolls-Royce and Daimler at the very top. As recent as 2008, they purchased the Catalite manufacturing facility in Mankato, Minnesota, as a place to manufacture their generator sets. A lot of questions come, is Catalite still around? They kept the name Catalite where the brand made sense, primarily in the ag markets in southern Minnesota for confinement turkeys, pigs, and that kind of thing. They had a very strong presence down there, so now that product will say Catalite by MTU, On-Site Energy. So that's a little bit about the history of our line. We offer sets on the diesel side from 30 to 3,250 kilowatts. Transfer switches, we offer 40 to 4,000. Switch gear, paralleling switch gear, and a full line of accessories. On the natural gas side, this one actually is changing a little bit, and I'll explain that when I come to the other slide. But natural and LP gas, we have 30 kW through 125. We also have now 150 through 400 kilowatts in a standby configuration. And those are Doosan powered instead of GM. And real recently, we're going up into the megawatt sizes, but those are prime power generators, which we'll talk about a little bit in a minute. Diesel, like I said, is 30 to 3,250. Two brands of diesels used on the low end, 30 to 200 kW. We have John Deere engines. Above that, we have MTU Detroit. This is the one I mentioned. We're going a lot larger. This is very new, and actually I'll be moving into this product as my primary focus for the future, starting 1/1/13. These units are running on natural gas and low BTU fuel. They're designed to run all the time. This is more of a cogeneration product. They run on digester gas. We used to handle the Waukesha line. As of earlier this year, we no longer carry that because MTU has come out with their own. This product is tried and true. It's not a brand new product for MTU. It's been used in Europe for a lot of years. So it's a new addition, and my charge is to develop familiarity with the engineering community across our whole territory. So I'll be traveling quite a bit. Pretty excited about that. Here's kind of a snapshot of the 3250 to just give you an idea how big that thing is. Sitting on a truck. We used to have a fat guy over here that got in the picture. He was a truck driver, but we did a little creative magic and photoshopped him out. Just look at the height of that radiator against the height of the truck. I mean, it's amazing how big these things are. They're used in a lot of applications. This particular one is a data center installation, St. Paul, Minnesota, where multiple sets are parallel, again, to bring up the reliability of the system in a standby situation. Now, data centers also have a lot of redundancy built in. You'll see a couple of sets of fuel filters here, 2 sets of oil filters, a lot of little extra plumbing to make these things work and stay running. And by doing it this way, they can worst case scenario, if the utility power was gone, they could run these things and even change the oil and the fuel filters while the thing was running. That's the idea of the redundancy. We'll be talking a little bit about some enclosures in a minute. Here's an outside installation showing a type of enclosure with sound attenuation.
Jerry, I think this is too jumpy for you. I think if you jumped over a few of them. Yeah.
Oh, did I?
Yeah, there you go. So
Okay.
just use this up and down.
Okay.
It's a little bit jumpy.
Okay. Let me go back a little bit.
I think you would start with the diesel, yeah.
Okay. Thank you. I thought it was doing that.
Yeah, I know. It's just jumpy. It does that to me too.
All right. We'll go manual here then. This is in a site downtown. Again, it gives you an idea of the size of some of these things. This particular one is I believe, a 3 meg set or 2.5 meg set, arriving on it's a double drop truck to get under the bridges and stuff. Here's another one with a different type of an enclosure. It's going into a Target store. You'll see a lot of these things around, and this is the typical way to get them into place. As you'll see the crane there with some slings. It's usually an exciting day when they come in, hoping that the contractor put his pipes in the right place in the concrete. So cranes are very expensive. Again, a different style enclosure. This is a smaller unit, and I'll use the pointer here for, this is actually an upduct, this portion of this enclosure. So in a generator set design, you have a fan that operates a little differently than the one in your car. When you're moving down the road in your car, the radiator brings the air in and it moves across the engine, hits the firewall, and goes underneath. Well, when there's no motion, you have to create an airflow. And all they do is make it, instead of a sucker type fan in a car, they put a pusher type fan, and the air is pushed through the radiator to cool it. And that creates a negative pressure inside a generator enclosure. So they can put inlet louvers, which is what these are, anywhere on this box. And because it's a pusher type fan that's actually pushing the air out of the enclosure and up in this case, it creates the negative pressure and sucks air in on the top. And they actually put baffles in here as a form of sound attenuation. Anytime you can, sound travels in a straight line, and anytime you can turn that direction, you also reduce the noise. So there's a lot of science in the actual enclosure itself. On the control side, we offer, on our units, we have a digital controller that meets NFPA 99 and NFPA 110 requirements. It also displays all the engine and generator operating parameters, oil pressure, temp, and that kind of thing, plus voltage, current, and kilowatts. Also has communication port, and that's how it talks to the remote annunciator. This is what it looks like. And a description. I'm not going to go through everything on here, but it's got a liquid crystal display and menu navigation system to where you can get to all of the parameters and whatever you want to see relatively easy right from the front. The annunciator, again, the RDP stands for Remote Display Panel. This gives you all of the NFPA 110 required functions for annunciation, plus a sonic alarm. This shows a surface mount, but it can be surface or flush mounted. Fuel types. This is where it gets a little interesting. Fuel considerations. When you design a generator set, these are some of the things you might want to be thinking about. A natural gas generator, it's consideration. The pros in this particular fuel is you don't have any storage issues. It's city supplied, it's always available, so that's a plus. It's also lighter than air. If there's ever a leak, it's going to go up. It's readily available. It's clean burning, and it can have an automatic propane backup. And that's done because of a National Electrical Code requirement. You have to have a 2-hour on-premise supply. And in California and other seismic areas, it becomes very apparent that you could actually, in an earthquake, rupture that natural gas line. So the option to make this system a legal system is to have a propane backup that'll automatically switch over in the event of a rupture. And it does that through pressure sensors in the lines and stuff. On the negative side for natural gas, it's a low BTU fuel, contrasted to some of the others. 1,000 BTU per cubic foot is typical from the suppliers. Some duration may be needed, contrasted to propane. Service interruption is possible. Propane. And basically the propane is the same basic carburetor as the natural gas. It's set up a little differently, and because it's a higher BTU fuel, it's adjusted a little differently. But on the pro side for propane, it's very clean burning, stores well. It's available on demand from your fuel supplier. It does, like I said, it's got a higher BTU content. It's 2.5 times more energy than the natural gas system. And it can be taken off as a liquid or a gas. And I'll get to that in a minute. Well, right there. Looking at this, typically in warmer climates, you would only be using a vapor takeoff. And because this liquid is under pressure, there's a lot of pressure in the vapor here. It's got natural pressure. So you open that valve, that gas is going to come out of there. In cold weather climates like we have here and in North Dakota, we've seen it along the I-90 corridor a lot. On extremely cold days in wind, it gets hard for a generator set to run because this tank cannot vaporize enough fuel to run the generator set. It's that cold. So what they do as a contrast is they offer a liquid takeoff that brings the liquid up through here, and they vaporize it externally, sometimes with a water jacket heater, heat exchanger type of a system, and that warms up the fuel into a vapor state, regulate it, and send it into the engine as a vapor again. Just a different way to do it. And it also allows you to, there's two ways to fix that problem of not being able to vaporize enough fuel. One is to use it like this and use a liquid takeoff, and the other is to get a much larger tank and take the vapor off that's available, one that might have enough vapor to run the set. This is a more cost-effective approach because it allows you to keep the tank size down. On the con side of propane, propane is heavier than air, and it will settle in low areas if there's a leak. When I was in Oregon, I did a lot of mountaintop repeater sites, radio repeaters, and a lot of telephone companies have repeaters on the top of the mountains. And there was one installation where they had a propane unit inside the building. And this was back in the days of a lot of relays instead of highly digital. And they had a propane leak. Luckily, this was an unmanned station. But the propane leaked and that vapor filled up the building, and then one of those little relays clicking obviously will make a spark. Took the whole unit right off the top of the mountain. So that's a big negative for propane. And I always tell engineers, make sure that all of the tanks and everything are outside and never bring liquid into a building. So you do the vaporizing, if you're going with a liquid takeoff, you do the vaporizing of that system outdoors. And then everything, hopefully not in a low area. Keep it up on a hill, higher area for locating the tank and stuff. So real life issues. This is what a typical natural gas piping system looks like. First of all, in the pipe, and this might be 2 psi out here. You know, that's a very common supply line like you might have in your house for natural gas. Got a manual shutoff valve here, a strainer, which heavier particles in the fuel will drop down here, and you clean them out every now and then. Comes on up again 2 psi into a primary regulator, and that regulator on the inlet here is 2 psi, and the outlet is 7 to 11 inches of water. That's the size we like to see. Comes around, and anything connected to an engine generator is going to have flex, even the gas line. So we've got a stainless steel braided flex section here, and that's because the engine rocks when it starts, and it's going to move some. And these three components are typically engine mounted. Got a, I said 12 volt DC solenoid valve, and that's going to be activated from the start signal on the generator. It's going to click not only to start cranking, but also open up this valve to allow the fuel to start to flow. The secondary regulator here, which knocks down the pressure a little more and then feeds it right into the carburetor. Okay, moving away from the gas system into diesel. The pros for diesel, it's a high BTU content fuel. It's got low volatility. Uh, doesn't ignite real easy. So it's slippery though. And it's readily available from suppliers. On the con side for diesel, the storage requires some maintenance attention because after several months of sitting in a tank, it will start to do some bacterial growth in it, so it requires some maintenance. Storage does require dual containment. Basically what that is a tank within a tank. Years ago, how that came about, you might have seen old gas stations digging up their fuel tanks. What happened years ago was they buried a lot of tanks and they didn't really think about electrolysis. But electrolysis began to operate on the skin of that tank. You actually got a current flow, and that actually caused a contamination and rusting over time on steel tanks, and it gradually began to leak. So that's what prompted the EPA to get into dual containment, and it's actually a tank within a tank. So if you see tanks buried today, and they still do that, they'll either bury it in a concrete vault with some gravel and pebbles and stuff like that, and then the tank sits in there, and there's sensors to tell if it leaks, or they do what the diesel manufacturers are doing, just putting a tank inside a tank with a float switch. The tanks, if you think about that, they're never going to leak because they're not buried, and there's no electrolysis acting on the tank. You might get a leak from a broken weld, but that's about the only way, so it's going to leak. But we have to meet the codes and satisfy the code people. So it's a tank within a tank that's enunciated with leak detection. Moving on to other cons for diesel, it's cold weather. It may require some additives to keep it fluid. Truckers a lot of time will add some cetane, keep the fuel from gelling, and so on. And light loading a diesel may require more maintenance. Again, on those mountaintop sites, phone companies said, they came to me one time and they said, we're really happy with this generator that we got. It's an old one, but it didn't cost us much. But we're having some problems with it. It's got this stuff on it. We want you to look at it. I said, all right. So we went up to this mountaintop site. And there was black juice dribbling all the way down the side of the block. And what that was it's unburned fuel. Same with light loading. If the diesel is designed to run under load, and the temperature is directly proportional to the amount of load that's on the set. So if you don't get that engine up to temperature, they don't have gaskets like a gas engine does. The machine surfaces don't fully make up, especially the exhaust manifold. So, and a diesel's notorious, it doesn't burn all the fuel. It actually returns a certain amount of fuel to the tank. There's a line for it. But when it gets up in the exhaust manifold and it doesn't have complete burning, it starts to dribble down the side of the block, and it's black juice. They call it wet stacking, or slobbering is another term for it. So light loading may require more maintenance. They asked, what can we do? We don't want to take this set out. We wound up putting instead of buying a load bank, which was kind of expensive, I said, well, just buy an electric furnace. It was small enough to where something in that range would put enough load on that engine to get the temperature up so it'd run. So that's how we fixed that one. Other common options on generator sets. Generator enclosures. We looked at a couple already. Kind of go through these again. We offer, this is a standard weather enclosure. And on this one, it's just got doors on the side. So obviously there's an open louver on this side, on this end, and an open louver on this end, and inlet and outlet. And you can see that the muffler is probably inside. This is a little rain cap that's sitting on top. Clean little package. This one, this is a good one to go over some of the things I was just telling you about. This one has the muffler on top. It also has a dual contained tank. So inside this black part, there's a tank that's down in this area, down to here, and up in here. There's some standoffs on the bottom that hold it off the bottom, so it's actually up and out. And there's actually a float switch that sits down in the corner of one of the corners here. I can't remember which one it is. But it comes down and just sits in there. If there's ever fuel in it, it pushes the float up, closes the circuit, sends an alarm. Also, this one's got an external scoop. Again, this is for some level of sound attenuation. We've got inlet air coming across the unit this way. A radiator sits about here with a pusher fan that's pushing it out and up. Again, we're turning the air up as another means to reduce the sound. Big deal these days in cities and so on. They want them to run quiet. There's a little step. Some of the tanks, because it's a tank within a tank, they get a little taller if we want to keep the footprint the same. Again, here's the other one we looked at before with inlet louvers on the top. The air comes in and goes up and around and over and through and then out this way. Here's a little different design. This is a Target store again. In this one, we're turning the inlet air as well. The inlet comes through here, across the generator inside, baffled out, and moves up. So those are the only louvers. It makes for a very clean design at the site, and a dual contained tank. This one's up at Northtown. Same design. There's different ways to sound attenuate and make it quiet. There's some baffles on the inside of this one that actually reduce the noise level. And that's an inlet air that you're looking at there, and we actually turn it inlet air here and down on this end. This section here is the up area where we're directing the air up. There's a brick wall around it again, and in hopes to keep it as quiet as possible. They've got a couple of these up there at Northtown. This one's at a hospital in Hutchinson. Same idea. Here we have sound baffles going this way. So we've got a radiator that sits about here, and it pushes out through sound attenuators, and it comes out the end already reduced in noise. Another thing that cities will be doing, they have a multiple voltage need. These are sold primarily to municipalities. These two little plugs here are for the water jacket heater and a battery charger. This particular unit sits as a standby at a particular site. So it'll operate totally as a standby emergency generator most of the time. If there's a situation where there's a widespread outage, this thing can be, these can be pulled out, and the unit can be taken to any one of a number of lift stations. And they actually have, behind the door here, there's actually a voltage selector switch, so we could probably go from 120/208, 120/240, or to 277/480 just by changing that switch. It's very common for municipalities. It's a handy setup for them. Water jacket heaters. There's a code in the NFPA for legally required engine generator sets. It says that thing has to be started and transferred online in 10 seconds. So that's a pretty hefty requirement. So even in summertime, you're going to see, especially diesels, will have water jacket heaters plugged in all the time because they've got to come on in 10 seconds by code. And the large V engines, and there's a lot of them, will have one heater per bank. So when you got a V engine, you'll see two heaters. Smaller ones will have a tank type heater. A lot of these you've seen on cars and so on. Anything just to keep the temperature up. Battery chargers, again, if this thing's just sitting, just like a car, you might have a slight drain on the unit all the time if it's connected. If it's not used, it needs something to bump that battery up all the time. So that typically we'll have a battery charger plugged in. Just bumps it. This one's a 24-volt charger. Again, an NFPA 110 requirement. Also has an alternator on the engine. So once the engine does start, you've got a quick recharge, just like you do on your car. So it's got two charging systems standard.
And Jerry, these will be fit from a 20 amp circuit external from.
Yes.
Okay.
The chargers are all that way. They can be from a 120 circuit, and we will furnish.
And the jacket heaters, they come typically 20 and 120 or different voltages? Or?
It depends. The larger you go, you got to look at the wattage on the heater, and that might crank the voltage up. The smaller units down around 100 kilowatts, usually maybe 1800 watts tops, and we'll use a 120 circuit. But anything larger, you get into some of the larger V blocks, then you're going up in voltage. You're running a 2-pole circuit because the current draw on the heater. We've got 12 kW of heat on some of the big ones.
Now, is there any talk, just like cars, of maybe going down like a hydrogen fuel or something?
Not on sets at this time. So but it's being experimented with. Some of the large manufacturers are toying with hydrogen. They've got some beta vehicles out there. So I would say that's a possibility. Probably a long way in the future, though. Some of the other alternate fuels are what I will be getting into this next year. No, primarily more common would be methane from wastewater treatment plants. The neat thing about the application there for wastewater treatment plants is it takes the methane gas, they have to condition it some and get the water out of it because it becomes hydrogen sulfide, which is damaging to an engine. H2S becomes sulfuric acid. But they clean it up and they feed it into the engine. They're actually, if you think about it, eliminating a natural gas requirement and using a free fuel off the digester. Okay, and they're producing electricity. So that's the true use of the term cogeneration. You're actually eliminating one utility, in this case, the natural gas. It's a smart application. Europe's done it for a long time. Not that I'm a big European advocate, but they're ahead of us in this particular field. Vibration isolation. Lots of different kinds of isolation. Little units, when I was in Oregon, we did a lot of smaller units and used this stuff. It's kind of a waffle pad. It's got a neoprene skin on the top and the bottom and cork in the middle. But it sure works good. And we could cut that stuff up and make little isolation pads pretty easy. These eliminate the vibration between the engine generator skid and the structure that it's sitting in. And it's of most concern inside a building. Although in big generator set enclosures, we put spring isolators in as well. Because we isolate between the generator skid and the fuel tank that it's usually sitting on. Lots of different kinds. And some of these isolators, like this one in the back, it's got a little thing, an adjustment screw on the side. That's for earthquake zones. So they've got what they call seismic isolators as well. Many times in medium-sized equipment, you'll see these sitting between the engine and its skid. And that works well for vibration attenuation as well. All right, any questions so far? I've gone through a lot of options on generator sets. Any other questions that you have before we move into transfer switches? All right. I came up with this definition, I think, in the first presentation I gave here. I wanted to kind of define this. A transfer switch is a device used to safely transfer power to the load between two different sources.
Good light on that.
Hmm?
Good light, okay.
On here?
Yep.
Okay. Most common transfer switch, and we're going to see some of my drawings here in a minute. This is the load down here. This would be normal power here, emergency out here. What a lot of people have done in the past, before we had codes and stuff that said you got to be careful with this, is they would do things down here. They would, when the power failed, normal went away. They would do things down here, and they say, well, I can feed this in on a circuit breaker in my panel and backfeed the whole panel. Not a good idea. So a transfer switch will allow you to, when the power fails, starts the generator set. There's voltage sensors in here. Starts the generator set, and when it comes up to speed and frequencies, the sensors here see it, and they transfer this, and it transfers over in this way, effectively opening that circuit to the utility. The other problem that was created when somebody has power trying to do it their handyman style here, when they backfeed that panel, that's actually going out to the pole. And if you've got a lineman that's trying to fix the problem in an outage, you could knock him right off the pole because it'll work as a step-up transformer going in reverse. So anyway, it'll safely transfer the power. And there's lots of different kinds. We'll talk about a few of them here. The most common is the open transition, which operates just as I described it. It's going to transfer from normal to emergency, but in an outage, you're obviously going to be dark anyway. But if you think about it, and the utility comes back, if you were in that emergency position, say now, here's normal. And we're over here now on the generator. Now we're in this position. Utility power comes back. The load is being supplied here. So generator has got it, but now we're going to see a blink in the lights because this thing is going to transfer from here back to here, but it's going to be open for a certain period. It's about 100 milliseconds, but you'll see a blink in the light. And older computer systems had a tough time with that little opening. Pretty much corrected these days. They've gotten their power supplies a little better. You get a little more ride through. And that's also the most cost effective, cheapest. Cost effective is a nice word for that. This is what I just showed you. This is what they look like. This particular one is an Asco switch, very common brand. Here's what they look like. Basically, the main switching part is back here, the contactor, and it'll have three landing areas. The feed from the generator down here, utility back here, and load here. And it operates just like we showed in the one-line drawing. Pretty simple. It's just got the contactor here and then basically the control over here. And this, I think, is an exerciser clock. which automatically starts and stops the system, and you can choose to transfer or not transfer the transfer switch in your testing times. All right. Post-transition switch. This is a little more expensive than the open transition, and I will change this from could to will require utility protective relaying. Especially Excel is very interested in seeing, because we're actually paralleling with their grid. They're very particular about anybody paralleling with their stuff. It's not for all types of loads, and you will not see a blink in the lights when it goes back to normal after an outage. This is what it looks like. Again, the utility comes in here, goes through its contactor to the load. And this is showing it at the instant of transfer. Notice both contactors are shown closed here. We actually provide 100 milliseconds of close time, and then the utility contacts come open when you're on generator. Is that clear? Moving up the chain, bypass isolation transfer switch. This came about basically, I think it was in California. It's an expensive switch in that it bypasses the automatic contactor with a manual contactor. It allows the automatic portion to be worked on. Say it failed while an operator or an operation was going on at a hospital. That would allow the doctor to continue on emergency power if there were a problem with the transfer switch. I'll show that on the schematic here in a second. Because it has two contactors, it's going to be more expensive, obviously, than a conventional switch that has one. And it's used where manual intervention will allow functioning of the emergency system. A little more complicated in its design, but basically you've got two sets of contactors here. And notice that in either case, they're both connected to normal, this way and this way. This is the automatic switch down here. Notice that I've shown a contactor here, and it can be removed. It can be racked out. That will allow, in an emergency, using the emergency system to finish an operation that's in progress, always keeping load supplied to where it's needed, the most critical.
Jimmy, the top one will be the manual then?
Top one is the manual switch. So if there were an issue with the automatic and something happened, we could actually rack this one out and manually switch this. And there's a picture I'll show you on the next slide. This is actually the manual switch operator here. And this is the rack crank to bring out. You'll see the actual rack. You can actually pull the automatic switch right out of the bottom. Sophisticated, but expensive.
And this could be closed or open transition?
Yes,
Wow.
both. It can be either. Again, if it's closed, the cost goes up that much more. They're very proud of that. All right, the final one I'm going to show you here is a common one. It's an automatic transfer switch using a soft load transfer pair. This is actually breakers. Two breakers act as the transfer switch. And in a soft load design, the transfer is transparent to the load. It doesn't know anything happened outside of a power failure, obviously. It's user-friendly in utility curtailment programs. Again, the customer gets the flexibility of his load never gets interrupted, and it doesn't know anything's happened. And it definitely requires utility approval and protective relays. It's the most expensive design, but it offers you the greatest benefit as well. Very simple schematic here, showing electrically operated draw-out breakers. It's typically the way the system is designed. The building load down here, this can stay closed for a long period of time. Typically, it stays for a few seconds rather than a transfer switch. A closed transition switch is closed only for 100 milliseconds. This could stay closed for several seconds. So what happens is the power fails out here. This is a failure, and the generator set will come up to speed and frequency and close its breaker to this load. Before the generator starts, it also kicks this breaker open. So when the utility cannot come back and knock the generator out of phase. So that's the first thing that happens in the power failure. The utility breaker opens through power provided by the generator set, then the breaker closes from the generator to the load. When the utility comes back, it's seen by the voltage sensors in the switch, and it starts to synchronize the two sources together. When they come into sync, they're actually looking at the voltage and the frequency. And when both are in sync, this breaker will close and both will be supplying load to the building. And it can stay closed, like I said, for several seconds, and then the generator breaker will be forced open and everything is back to normal. And it can operate that way, again, for utility curtailment programs. They'll be synchronizing in both directions. So when the utility said, we want you to run your generator sets, again, the customer would start the generator and it would synchronize to the utility going to emergency. Then as soon as it was synchronized, the generator breaker would close and then the utility would open. Again, the load didn't know anything happened. And the reverse on the same process going back when the curtailment interruption is over.
If I may inject one thing here, next project that we guys want to do, we're going to have a 4,000 amp switch gear, and we're going to be using this method, soft start parallel switch gear.
Okay.
So just what we're using right now, Jerry, is we're using an auto transfer switch with. We're bringing the service to the auto transfer switch, so we need a service disconnect means. I don't know if you throw a few things, because that's the project that we're doing. We have a 500 amp 28120 building, feeding it to a gen and the service via an auto transfer switch. So bringing the service right into the auto transfer switch. So
Entrance rated switch.
Yeah, if you would say a few things. No.
Yeah, that requires an entrance rating for this device, and is primarily on the utility side. This becomes an entrance rated breaker. So it'll be service entrance rated. And again, then the load is in the entire building. And that's the most common place we see the soft load switches, and when we're taking over the whole facility. So this is a service entrance device as well. However, we have seen them in distribution where we've had critical load that the owner's been concerned with, so it doesn't have to be entrance rated at that point. This is what one looks like. This is one manufacturer's design. Again, the control up here. This was kind of a very clever design. This might be the utility here and the generator down here, the two breakers. The load connections were in the back. This is actually a Schweitzer relay, and it was one of the first ones that was able to be programmed right inside the relay, the ladder logic for the operation, eliminating an entire PLC which controlled the operation in the past. So that was pretty clever, and it was made by Schweitzer again. That's a very impressive unit. This is what it would look like sitting outside of a building. If you remember that super target picture before, It's the same one. The generator has now been set here, and it's like Chad was saying, here's the utility, here's the generator. We're going to feed them through this device, and the load is connected to the bottom. All right, those are transfer switches. Talk a little bit about different types of loads that you're going to see, especially in the nonlinear category. Nonlinear loads need diesel engines. I say this, it was only a personal preference. It's not a requirement. But if you have a heavily nonlinear load, it's best to have a diesel. And that's only because of how a diesel engine reacts to a load as opposed to a gas. Some of the nonlinears are very fussy. UPS systems especially look at the input, and if it sees any fluctuation, it goes to a bypass mode. Diesel engines are a lot stiffer in their reaction to that load. We don't have issues there. They also need special consideration and sizing because we've got higher than normal neutral currents flowing. Types of nonlinear loads that you're going to see are UPS systems, battery chargers, VFD drives, which are becoming more and more common on motors, and T8 ballasts and fluorescent lighting. Nonlinear effects can be offset with other loads. A good example of that is Time Warner Cable, when it was still Time Warner, called me in. Their engineers were having an issue at the Eden Prairie site, and they had just about 100% nonlinear on there. And for a test, I kind of suspected that based on what they had already told me. We brought a portable load bank with us. They were having problems getting the generator to stay running, and it was hunting. And what it was doing was the UPS was causing, because there was so much, the actual waveform was notching because of all the firing of the SCRs. Well, this particular site didn't really have a PMG excited alternator. So that's one potential fix. But they coupled this output back the way it was supposed to operate. Is the AC, it was looking at an amplitude primarily, and this output was coupled back to the voltage regulator. Now the voltage regulator is looking at these things and saying, what the hell? It's what it thought was zero crossings and trying to chase it. So we had this fluctuation. Well, we offset that by putting different types of loads. We wanted to get rid of as much of the notching on that wave as we could. So I brought a load bank with me, and I told them also to connect some air conditioning to it before I got there. And air conditioning was just a regular motor. It wasn't a nonlinear. And the addition of those loads against the bringing up the linear load with the nonlinear kind of damped out the effects of those spikes and took the problem away. So the bottom line was, well, they just put some more linear load on the whole system, and that fixed it. Okay, UPS, uninterruptible power systems. These are used to maintain power to a critical load. It can be a computer or anything else that customer deems as critical. It never loses power, and it's typically a data center today that's using this kind of a system. I can't remember if I stole this or if I came up with this, but a UPS is basically made up of three parts. A battery charger, which changes AC to DC, charges the batteries, keeps them charged up. The batteries themselves, and then an inverter, which changes the DC back to AC and powers the critical load. So if the power fails here, we still have the connection to the battery, so the inverter is still going to work, right? So the critical load has seen nothing happen. That wave is still there. That gives us a chance over here to start our generator set, transfer power, boom, replenish this. Now this battery charger fires up and it's replenishing the power that it took to run this load while the power was off. So virtually uninterruptible. What that does, in effect, is it takes the time that critical load is now functioning without utility from the battery, the amount of time we have on a battery, to the amount of fuel we have in the tank out here in the generator set. And then the outage can be any length of time and you'll be good to go. Other motor loads: air conditioners or rooftop units, chillers, elevators, pressurization and exhaust fans, spark pumps, fire pumps, all have their own requirements. Fire pumps especially, there's some codes. They can't dip more than 15%. Lighting loads: incandescent, fluorescent, and discharge lighting. Discharge used primarily in warehouses and things like that, outdoor lighting. All right, moving into two basic building designs. We'll look at a one-line drawing of a partial building where only the critical load and some additional loads are picked up by the generator set. And then we'll look at taking over the entire facility.
Jerry, shall we give it 5 minutes break?
Okay.
5 minutes. We take 5 minutes break, guys, stretch a little bit? Okay, that's probably, if you're okay with this?
Yep.
Thank you.
Take 5 minutes, guys, stretch yourself and let Jerry clear his throat a little bit.
I've done a lot of these in my time.
Yeah, show and tell. Isn't that cool?
Yeah.
That's nice.
Well, your larger generators, what size is your mounting pad then?
They get pretty big. It depends on the type of enclosure that you put on it. With the really critical sound attenuation, they get very large. Could be up to 40 feet.
Is there any consideration on what type of concrete you're supposed to use, any regulations on that?
Yeah. I rely on the mechanical contractor a lot there, but and the mechanical engineer, because we'll give them the weight and they know how much the fuel is, and they take all of that into consideration and they calculate how thick that pad has to be, and if it's in cold climates, if it needs footings and that kind of thing.
Yeah, there's more to it than just pushing the
Right.
big one.
That cushion pad, I've seen that. I've actually used it at the place I used to work. The mounting. Use it on a couple of our machines.
Mm-hmm.
And then 30 tons of cheese. 1 inch head really actually does a pretty good job.
Yeah, it's amazing how good that stuff does work.
For that Time Warner location, do they have natural gas generator? Is that why
No, that's actually a diesel,
we're still having problems because it's so much linear?
because they had so much nonlinear. Yeah, PMGs actually, it's a different type of an alternator. A lot of them you can add a PMG if you use the right kind. Like a Marathon makes a PMG and a non-PMG. And the non-PMGs use that feedback where they couple a portion of the output back to the voltage regulator. Well, the PMG doesn't have that. It just looks at a constant reference that's made off of a DC signal. It makes its own little sine wave in the regulator. much better way to go because it's not affected by the notching in the way of them. So,
What's the cost of the generators?
between 250 and 350 per kW. An average. And more complex, obviously, more you tend to run to the high end. The other ones, like I'm looking at getting into where they run all the time. Those engines are a lot more substantial, and they could go up close to $1,000 per kW. They get very expensive, but they're designed to run all the time.
We go here, we're good, and I'll fire it. Oops. No, we don't want to go buy things. There you go.
Okay,
I can move this one away from you as it sits here, just tiny at the bottom.
all right. Okay, let's take a look at the partial. How come this thing isn't?
It's not, we might have to click it the first time this way. There you go.
Okay, partial building. There we go. In this scenario, okay, we see the UPS we just talked about, providing power to the critical load, sitting over here. That's in distribution. And in this scenario, this is actually our emergency distribution panel because it's downstream of our transfer switch. The way this operates, and it looks like we've got some spares here. We've got a data center RTU. So we've got our air conditioner for the data center room, the UPS room. And we've got some emergency lighting. And the way this operates, under normal circumstances, the utility comes through the main distribution panel. It has a feeder breaker through the switch to the load, feeds the emergency panel, and the UPS to the critical. When the power fails, transfer switch sensors will see it here that it's gone, start the generator, bring it up speed and frequency. When it's there, the switch will see the power here, switch over, and the generator is supplying load to the emergency distribution panel only. Again, way out here in the critical load, it doesn't know anything happened. That make sense? In the entire building, back to this drawing again, we look at our soft load switch. Again, in this situation, I drew this as very simplistic, but as Chad pointed out, this is now a service entrance device where we're taking over the entire facility. So this isn't a service entrance rated soft load switch here. Power comes in through the utility main, feeds the load. In a curtailment period, power is still here, but we start the generator set, synchronize with the utility, close this breaker. The load doesn't know anything happened. utility main opens, and the utility can now use that power that was feeding this facility elsewhere, instead of wheeling in power from another source additional. Other considerations. Okay, when we design a system, there's a lot of things we have to think about. UL 2200. This was a UL listing for generator sets that came into play in 1998. Pertains strictly to the manufacturers of the generator sets, and it tells how the set is going to be shipped from that manufacturer. It's for stationary applications only. In other words, no mobiles, municipal sets, that kind of thing. 600 volts or less. So medium voltage doesn't get a UL 2200 listing. Open or enclosed units, doesn't matter, and it's any fuel. Changes to multi-voltage block heaters, battery boots, those are some other things that are required by UL 2200. Noise. This is a big deal. Many municipalities, I would almost be ready to change that to all municipalities have noise ordinances. It's usually enforced only when there's a complaint. As I said earlier, noise travels in a straight line. It can be attenuated many different ways, and it will continue to be a concern in the future as long as we have an EPA. The reduction may be required by code, usually is. And the ordinances can be found a lot of times right on the city's websites or county, whatever municipality we're looking at. And the degree of noise reduction must be quantified, typically measured at 23 feet. Why they pick that distance, I don't know, but it's 7 meters or 23 feet is how generator manufacturers usually define their quantitative noise. And engineers need to specify the method of verification of compliance. And reducing noise does cost money, in fact, a lot of money. Some rules of thumb. Doubling the distance from the source, in other words, from the, let's say, the generator set, sound is reduced by 6 dBA. Minimum starting distance should be 23 feet. I added that note later. Example is a generator with a noise level of 80 dBA will have a noise level of 74, approximately 50 feet away. And it's an exponential scale. That's why these rules will work. 2 equal sound sources increase the overall sound by 3 dBA. So 2 at 80 will be an overall combined noise level of 83.
You would think they will double the noise.
Yeah.
A lot of people would think 2 generators will double the noise.
To the human ear, twice the loudness is a 10 dBA increase. So 80 is sounds twice as loud as 70. A couple of charts I threw in that I've run across in my career. This one I think I got from Cummins. Frogs croaking is at 60 dBA. Drizzling rain is 50. Low voice is 40. Birds singing. Notice thinking is 0. Falling feather is 0. Mosquito in flight, 10. Kind of fun stuff. Another one here. Rock music, 120. There's a threshold of pain up here. That's some fun examples. All right, moving away from noise into an area that's becoming more and more prevalent. I said noise was costly to attenuate. This is even more costly. And there's been a lot of terms that have come to pass over the years, and I'm kind of the emissions guy for my company. So I forgot to take a step backwards when the volunteers were asked for. But I took it on, and I'm kind of following a lot of these things for our 10 states. And it used to be a lot easier to sell generator sets. All right, a couple things on emissions. We're not going to get real deep into it. It's ugly. But as far as this presentation is concerned, this is a talk that I give to consulting engineers as well. We're going to be primarily concerned with emergency standby power, and basically these are kind of lumped into all others, non-emergency. This was redone in 2011 by the EPA in this standard. 2000 EPA actually redefined what we call emergency generators and non-emergency. It made only two distinctions now because of this ruling. An emergency is basically what it's always been. Standby, the true standby, where the utility fails, generator runs, and then utility comes back, it transfers back. That's true emergency. Non-emergency is everything else, and those things that are non-emergency examples: peak shaving utility programs. This has a lot of people upset. Storm management. What that is a lot of companies, many times, that had generator sets, if they saw a thunderstorm coming, rather than take a break in power when they weren't expecting it, they set their equipment up to where they wanted it. They could accept a transfer, and they would actually run their generator set. They call it avoidance, interruption avoidance. So storm management is another term for that. Prime power, where there is no utility, is non-emergency. UPS configuration and extensive testing applications. Here's the actual code, and I highlighted it in red. This is the definition for emergency now. Emergency stationary internal combustion engine means any stationary internal combustion engine whose operation is limited to emergency situations and required testing and maintenance. So that's the standard definition for emergency. It says that you can run your system basically 100 hours per year, but there's no time limit on the use of emergency generators in real outages. That's why you have the thing. So that's emergency. And with that, they came up with a set of emissions that we'll look at in a minute. And what does that mean for us? No modifications to our equipment at MTU. Current production line, product line will remain the same through 2014. No exhaust after treatment is required for true emergency. And this is what the emissions look like. Over here, they've got the horsepower sizes of the engine, basically. KW is not electrical KW here. This is mechanical to equate with horsepower here in this side of the chart. And these are the compliance dates and the emission levels that back here was Tier 1, for instance. 2007 brought in Tier 2 for this size right here. And notice that some of the bigger ones are Tier 2 even today. So the horsepower of the engine will determine what tier level it's in. So but we're basically here, 2012, and we're in compliance with all of our product line right now for emergency. There's no issues all the way through through the end of 2014. Non-emergency. I took that same definition. Oh, this particular slide, I was mad. Stationary compression ignition internal combustion engines used to supply power to an electric grid or to supply power as part of a financial arrangement. This is very specifically talking about utility curtailment programs, which are great for business. They said these are not emergency. They wanted to spell that out very definitely. So now, when we look at non-emergency, what does this mean for Detroit Diesel Products? Exhaust after treatment will be required. There's got to be a NOx catalyst strategy, and that's done with an SCR, which is not a silicon control rectifier. It's a selective catalytic reduction, basically a catalytic converter like you have on your car, plus, because we inject urea. And minor modifications to the current engine. I put this last one in, that's again an opinion. Must be supplied as a package from the factory. What I'm saying there is this stuff that we put on the engine, if the manufacturer is going to back it, they're going to want to supply it if they have to be held to it. So that's long range. The chart looks a little different for the tier level requirements for non-emergency. Everything right now, you'll see the blue, which is where we are in time. We're in 2012. Anything for non-emergency has to be tier 4, which is a very stringent requirement. So what we're seeing is a lot of utilities are upset with, they had programs set up with their customers that now they're being required to upgrade their equipment to meet these emission levels. Not real popular. What will these changes require? Here's a tier 4I, and I in this example stands for interim because it's not the final level. But basically, this selective catalytic reduction this is all external to the engine now. Okay, this takes into account that we've done everything we can on the inside the engine, and we're taking that exhaust and we're dosing it with some urea here, and there's a mixing element that goes on that produces ammonia and steam, and that whole product goes across this catalyst, and the output of that is water and nitrogen. And this the SCR primarily targets NOx, nitrous oxide, gets rid of it. This is what it looks like graphically. The nuts and bolts of the system get pretty complicated, so you can kind of see that adding these components to clean up that exhaust for NOx, this is again is NOx only, can be kind of spendy. You've got a tank here for the urea. The urea also in cold weather like we have here has to be kept warm because it crystallizes at a lot higher temperature than we have normally here in the winter. So it's another issue. Installation considerations. This is some of the equipment, the SCR housing that's going on that unit now. This piece here, this dosing is the urea coming into this chamber. Exhaust is coming in this way, being injected, and it's going through here and it mixes in this section and then goes across the catalyst at the exit. Again, this cold weather concern, 32.5% solution of urea, it's actually a liquid, starts to crystallize at about 15 degrees. So now we're heat tracing tanks and lines and stuff to keep problems with freezing out. again, a lot of control, a lot more things to be concerned about with your engine. Here's what some of them look like. Notice that they're coming up through here. Here's your SCR here, and then through the silencer finally out the end. Indoor applications here. Again, a lot of these installations have to be engineered in the field as well, because for retrofitting existing equipment, it can get very expensive. Yeah, I'm not going to go through all of these bullet points, but it's amazing. This is the cost impact. That's what we have. Questions on that? Emissions are going to continue to be a big deal. There's another program with emission, in addition to new engines, that looks at existing equipment, and it primarily targets, instead of NOx, targets carbon monoxide, and that is a catalytic converter. So we're doing, and I'm kind of heading up that program for Interstate as well. Okay, we'll move on. Did you want to try, did you want to continue and do some sizing?
You will walk them through what you guys have in the binder here.
Oh, okay.
And then that calculator, and then maybe we'll walk them through the software quick while I fire it.
Okay,
Would that be good?
that'd be good.
Okay. We'll wrap it up.
Okay, a couple pieces. This is a piece that is actually put out by our company. It's in your packet. On the back, you'll see all of our branches are listed on here. It's called Diesel Today. And this comes out, and it's a good piece that I give to engineers. Not only talks about generator sets on occasion, but all of the emissions issues that face engines today. You'll see some things in here on that. A lot of the customers that we have with engines in it, you'll see a cement mixer, a lot of different things are highlighted in there, and all of the applications for the MTU engines. So it's kind of an interesting piece. See, we've been working on Loram. They make rail grinders. They're here in Minnesota, up in Medina, and they ship their rail grinders all around the world. They keep the tracks level and conditioned.
They're coming here Thursday.
Really?
Recruit.
Really?
Yep.
Loramin.
Yep.
Very good. This is a brochure on our company, Interstate. Again, I like giving this one to consulting engineers. Shows them the cross section. There isn't any part of a truck, which is our base business, that we can't take care of. We do. We're a distributor for Carrier air conditioning for refrigerated trucks. We also have a division that leases truck trailers. So, kind of a blurb on our company. In the back portion, the very back, is where you'll see some of our sets and some of the applications where we put it. Then we've got a little slide rule for you. It's kind of a handy tool. Gives you the voltage. I think that's pretty self-explanatory. Voltage and current can be calculated, kW on the back. Wish I had one of these when I was starting out. Those are handy.
Software spec? I have comments, right? Is that okay?
Yeah, we'll look at comments. Might be a little rusty on it, but
Okay. Now they use the software. They already use the software.
Okay.
And did a couple of things. Maybe just overview of the importance of the load and the steps. That's probably would be a good, really, a difference between the loads and what a step means when you add it to the motor.
okay.
If that makes sense.
Okay, they're already using this. We've got a new project here.
Do you have views online? We can open it in the existing one and look at it.
Or
Or you gonna, okay, you just,
We can do this, I think. I remember how to use this. Basically, start with the step. Here's a UPS load. And we can go with, we'll plug in a 25 kVA UPS. A rectifier pulse on the UPS kind of is how the power supply operates. A 6-pulse rectifier is a default. 12 would be a much better. So we'll go with, we're not sure who's going to be supplying the UPS, so we'll go with a 6-pulse. Maybe I should define the project too. That's a
so Jerry is gonna walk you quick through the software that we use and give you his 2 cents on, which is a lot, about how to use the software and the impact of the software and the size of the generator that you have. Because I know you guys have used it, so, but the impact of what you pick here on the size of the generator and holding that.
okay. Let's put a few steps in here. We'll just call this all right. We'll put some more loads in here. I'm just backfilling some loads and we'll talk about these things here. Motor, we'll put in a 50 horse. On motors, it's very good to look at the type of motor and motor starting that you have. Help me out here, next. Cross the line. Okay, here we go. This particular box, you're going to see on a lot of the larger motors, chillers maybe in large buildings might have a VFD type of drive or a solid state starter. Those are very common ways to get a motor running with the least amount of power. So they're actually pretty good with generator sets. Auto transformer, you'll see a lot in municipalities running big pumps at water departments and so on. Mainly use a 65% tap most commonly. And that gets the power factor down, and it also reduces the starting power factor is the concern here. Get that motor running for pumps. So we'll put in a 50 horsepower with that on. Some other lighting. Gotta have lighting. Put on about 10 kW lights. Fluorescent is fine. Let's put in 277. Single phase. Okay. And we had a 25 kVA UPS motor. And we better try a fire pump too. And this, we've got a bigger building, so we're going to have a 75 horsepower fire pump at 480. Okay.
There's option for VFDs there.
Okay. I don't know if the Cummins program is intuitive on that. We'll find out. On the fire pump, you have a 15% maximum voltage dip requirement. And we're going to see if they take that into account. And we better throw on a chiller here too. Oops. Variable frequency drive. Okay, chiller. That's enough. And we'll start loading these into steps. UPS, we're going to want step 1. Okay. Chiller, we'll put step 2. Step 3. UPS motor. And fire pump. Be the last one. Okay. Okay, they do know. For fire pump loads, the peak voltage dip that occurs when the pump is operated must be limited to 15% or less to meet code requirements. The peak voltage dip in the project parameters will be reset to limit dip at the generator terminals. You may want to limit this dip further to account for any appreciable line drop between the generator and the fire pump. Good comment. Okay. Now, how do we get it to, oh, that's this one? Size it? Okay. Based on the loads that we plugged in, it picked a 230 DFAB, and you'll notice here that the voltage dip is 15%. It's limited that to the fire pump, and it's also picking a larger alternator. It's 105 degree, and it's got a PMG for an exciter, which are additional motor starting load application enhancements. It's got a bigger generator and it's PMG. This particular program also tells you the percent of the nonlinear load, which is a very good thing to know. Now, the owner can't afford that. He's saying, well, I'm not so sure that we have to put the fire pump in. What do you think? So they check and they say, okay, we'll take the fire pump out. So now we'll go back and we'll completely remove this, delete that step. So we don't have a fire pump in there. Now we'll go back, resize it. It still picks a 230. And it's saying they've only got a voltage dip of 6% here, and the load could go up to 35. And you can reset, you can set the parameters up in the beginning of the program to be anything you want as default. 35 is a little heavy. You could have motor contactors dropping out at that. So bring it up to 30 or maybe 25 would be a good design parameter. So I don't know. I don't know if they
Is the load running?
huh?
For load or what?
Yeah, I wanted to get out of there. Okay. Do we have a place here we can look at view?
Project?
Yeah, view the steps. Oh. Okay, I want to see the running KW. Okay, the chiller actually is what's driving the size here. We've got running KWs here. It's always good to look at to double check the program. So we've got 70, 80, 140, 220. It's sized pretty much right at the end, the maximum. We've got a total running KW right near our generator size. So we might want to bump that size a little bit. And that's it picked a 230, so I would say, let's go back to sizing. Percent nonlinear. Does it have a total percentage load?
Load running the second tab, I think it gives you about load running in surge requirement.
Hmm?
I'm looking at the one.
You want a total running KW?
No, I'm looking at the amount of load versus the size of the set. Okay, alternator KW is 264. Alternator max is 300. Okay, so that's starting. Size. Running KW is 167. Okay. They used to give a percentage of this, so those are the two figures to look at. That's not bad. That's a good size for this model. I like keeping that ratio 167 to 230. These two values here. The total running KW is, we'll call it 170. 230. That about 70% of the load is a good size. That allows the customer in the very end to add load. They're all going to do that. They're going to put some things that they don't even have yet on emergency. At some point during time, they might buy more equipment. So it's always good to go 70% starting out. And it's a good question to ask in the design phase too. Do you have any future expansion plan? Data centers today are looking way down the road, and they say, well, we're going to double our capacity in about 3 years as they grow, and they don't want to do anything up front. So you have to account for that in your initial design to make sure they have that capability. Is there any other questions that you had on anything I covered today? Went through a lot. You've got my card. If you have any questions when you get into your projects, want some help, shoot me an email. That's going to be the best way to get me. I travel quite a bit now with the current emissions requirements of the day. So thank you very much.
Thank you.
Thank you.
Awesome.